Hello, welcome to our tutorial number 3 on classification. Today we'll be discussing probabilistic models. So a probabilistic model is something that defines a framework for machine learning that uses posterior distribution to classify data samples into respective classes. Now what do I mean by posterior distribution? A posterior distribution is if, let's say, we have a data sample X and a sample class Y. So the probability of this data sample X being in class Y would be defined as P Y given X. That is, if X occurs with the probability P of X, then what is the probability that if X occurs, then Y will occur. That is what probabilistic distribution is. Right. This also defines a decision rule. Now, a decision rule is basically a way to predict a value of y on the basis of values of x and posterior distribution. Right. This is a posterior distribution. Right. So, a decision rule is a way to predict y, the value of y on the basis of x and posterior distributions. Right. Now that gives us a decision rule. So now, as we have discussed what posterior distribution means and how do we create a decision rules, let's discuss what Bayesian machine learning is. So Bayesian machine learning provides us with two rules. Number one, it provides practical algorithms. Right. It provides many such practical algorithms like naive Bayes classification, naive Bayes, right? Then I'd say Bayesian learning, Bayesian network learning. This topic is exclusively taught in Comp 9418 Advanced Machine Learning. If you want to learn more about it, you can obviously opt for this course. And the second rule that is provided by Bayesian machine learning is it provides useful conceptual network, right? So it basically provides a basis for you to work on or to compare your models with, right? So you have heard of Occam's razor, which states that the simplest solution is the most general one, right? And this Bayesian machine learning provides you the simplest way to classify a data sample into a class. Now, before starting in deep on Bayesian machine learning, let's discuss some basic rules of probability, right? If I'm talking about basic rules, number one would be product rule. Product rule says that if you have P, A and B, this is given as PA given B multiplied by PB, or this can also be written as PB given A into prior probability of A. Similarly, that gives us our second rule, and that is sum rule. This is just a recap of all the rules that you must have studied before, right? Sum rule says if you have PA or B, this is given as PA plus PB minus P, A and B. Now this can be visualized as, right, in set theory, if you have set A, if you have set B, right? So if you want to find P, A or B, if you take PA, you take this area once. If you take PB, you take this area. So that means this little shaded portion is counted twice. Now this is nothing but A and B. So you just remove this once from the summation of PA and PB to get PA or B. right? That gives us the rule of total probability. Now, total probability, it says that P of D is equals to, or let's say P of B is equals to sigma of B given A I into prior probability of AI, where I goes from 1 to n, right? And AI are A1 to AN are events which are mutually exclusive. Only when they are mutually exclusive, this holds true, right? That brings us to the fourth one, the conditional probability. Right. The conditional probability says P A given B can also be written as P A and B upon P of B. Right. Where P A and B can further be written as P A given B into P of B, or P of B given A into P of A. In this case, we take this. Therefore, P A given B gives us P B given A into P of A upon P of B. This gives us your conditional probability. Right. Now, that brings us to Bayes theorem. So, in Bayes theorem, we start off with the formula. Probability of an hypothesis given data point D is given as probability of occurrence of data point D given hypothesis H, prior probability of hypothesis H divided by prior probability of occurrence of data point. So this is prior probability of data point D, training data point D. This is prior probability of occurrence of H. This is probability of D given H, and this is probability of hypothesis given the data point. Now we want the most probable hypothesis given the data, right? In order to find that, we introduce the concept of MAP, which stands for maximum a priori, right? Which states that we find an hypothesis H map, which will be max of all the hypotheses that are there given the data point, right? And now, what is a hypothesis? Hypothesis can be anything, like let's say there are three classes, x1, x2, and x3. There's this data point that comes in capital X. So hypothesis can be this x belongs to x1, belongs to class x2, belongs to class x3. So there are three possible probable hypotheses, right? So these H are basically the classes, the probable classes that are there, right? So we want to find maximum a priori H map, which is the maximum of all PH given D, probability of hypothesis given data. Now, how do we do that? Right. So we discussed that our H map is equals to argmax probability of H given D, the maximum out of all the H given D, Hi, like H1, H2, there can be various hypotheses, And let's say if your data D comes in, okay, so PH given D is just the probability that D lies in class H1 or class H2 or class HI, right? We find the class as the class which has the max PHI given D, right? So this can also be written as argmax PD given H into probability of hypothesis upon probability of D, prior probability of D. Now, as you'd see, for each HI, right, from 1 to N, let's say N, right, for each HI, P of D will be same, right? So, like, we can ignore this. If you're trying to find the max, that leaves us with where H belongs to capital H. Capital H is the hypothesis space. Argmax P D given H into P of H. Now, let's say we have a hypothesis space capital H, right? And there are these few hypotheses that are present in this space, right? So the probability of occurrence of each hypothesis Hi would be equals to the probability of occurrence of the other hypothesis, right? So if you take that, we can also choose to ignore this term because this will be always equal. This would, if you take, like, let's say there are n hypotheses uh, in hypothesis space, right? For each hypothesis, the probability of occurrence would be, or, right? Therefore, that leaves us with H map is equals to max for H belonging in hypothesis space capital H, P of D given H. So now let's rewind a little bit. So, like, we have this formula PH given D, which was written as D given H, P of H upon P of D, right? Now, as you know from total probability, P of D can also be written as sigma of uh, D given HI, P of HI from I equals to 1 to N, like the total number of hypotheses that are there. And this is for a particular hypothesis H. Uh, Now, I just want to introduce a few terms that, what is this? This is a posterior probability, that is true, but this is also called a likelihood of H given the data D, right? Similarly, this is also called the likelihood of D given hypothesis H, right? Now, we were discussing a hypothesis space capital H. Now let's call it a version space. Now let's have a version space, right? Now if we have a version space consists of your hypothesis and your data points D. Version space has small hypothesis spaces in them. Like, these are all capital HI, which are then forming of again smaller hypothesis HIs, right? Now, if you see, what would be the probability of occurrence of an hypothesis H that was given as mod of H, right? What version space is just a set of all consistent, non-zero or zero error classification rules, right? There can be many classification rules, but like according to our data, this HI is suitable for our classification problem, right? Now we have um, an instance space X and hypothesis space capital H and a training example capital D, right? So if we have this, so if you have a version space with hypothesis and data consistent to with consistent classification rules, we'll have P of data given hypothesis is equals to 1 if if our hypothesis H is consistent with data D, right? If H applies to D basically, right? And P D given H is equals to 0 if otherwise. Why I am doing this, I'll explain it to you, right? So if our hypothesis H is applicable to the data or is consistent with data D, our probability of D occurrence if H occurs is equals to 1, otherwise it's 0, right? We are trying to brute force our way using the map framework for concept learning, right? Uh, okay. Now we have a total probability formula which is given as P of D is equals to sigma of P of D given HI uh, into P of HI, where I goes HI is in hypothesis space H, right? If you're searching the version space, P of HI is equals to 1 of mod H, the size of our hypothesis space. So if I want to search the version space, we get P of D HI has two values, 1 or 0. So let's take both the values. Plus sigma 0 into mod H. This becomes 0. So if we are searching the hypothesis in the version space, we get upon mod of H. So our P of D becomes the size of our version space upon size of our hypothesis space, right? Now, if we use these to find the posterior probability of hypothesis given data, right? That means we had to find this, right? In MAP as well, maximum a priori. We want to find the maximum probability such that such the given data we have an hypothesis H. This can be written as D given H into P of H divided by P of D. This is given as, I'm not taking the 0 value for it because we just want the data that are consistent, hypothesis space that are consistent with the data, replacing the values back. Right, we get mod of Vs, the size of a version space that gives us the probability of PH given D if we have consistent H with data, otherwise 0. Why I want to show you is this, because when we take posterior probability, what we are doing is basically reducing our hypothesis space, right? If we have this hypothesis space and if I'm taking P of H, we have a very huge hypothesis space to search over, right? Like there can be many rules that can be applicable. But if I want to shorten down my hypothesis space and want to find a more accurate answer, what I do is I find H given D1 What that does is that increases the probability of H given D1 as well as reducing the hypothesis space. Now, if we talk about two data points, right, our hypothesis space becomes even smaller. So this gives us better results, right? This will be more accurate. If we have two data points D1 and D2, what is the occurrence of probability of H? Okay, so that completes the basics or the starting of classification 2. Now we are going to tackle the questions that are present in the tutorial, the PDFs. The first question, it says, consider the example application of Bayes' theorem on slides 21-24. If you have the slides, I'll just read out the question. So a patient takes a lab test and the result comes back positive, right? Um, Patient takes a lab test and it comes out positive, right? The test returns a correct positive result in only 90%, 98% of the cases in which disease is actually present. So if I want to write this down, I would write, okay, disease present, I write it as cancer and gives out a positive result 98% of times, so 0.98. And a correct negative result in 97% of the cases in which the disease is not present. So disease is not present and negative. So this would be 0.97. Respectively, this will give us positive and not cancer is equals to 0.03. And similarly, probability of negative given cancer is 0.02. Right. The last line says, furthermore, 0.008 of the entire population have this cancer. That means probability of cancer being present is 0.008, while probability that cancer is not present, it is given by 0.992. Okay. So the question says, does the patient have cancer or not? So let's tackle that first. If you want to find out that if a patient has cancer or not, what we need to do is we want to find the MAP hypothesis or the most a priori, maximum a priori hypothesis. So in order to find that, what we do is given cancer multiplied by cancer, right? This will give us 0.98 into 0.008, and similarly not cancer. You want to find if it has cancer or not, right? Uh, Cancer, this will give us 0.97, sorry, 0.03 into 0.992, right? When we compare these two, we find that this is greater. Therefore, probability of not having cancer given the task was to find that if the result came back positive, the patient has cancer or not. But when we calculated the hypothesis space given the data, hypothesis given data, that is probability of cancer given positive, probability of not having cancer given positive, right? When we calculated these two, we found that B is greater than A. Therefore, taking that as maximum, we say that cancer is not present. Right. Now, extending that question, we tackle the question given in our tutorial. It says, now suppose after this test, a second laboratory test is ordered for the same patient. And the test also returns a positive result. What are the posterior probabilities of cancer and not cancer following these two tests? Okay, now we have to assume that these two tests are independent, right? So, number one, assume tests are independent, right? And we have found out the value of P of plus given, I'm writing C for cancer into P of cancer, and positive given not of cancer and P of not of cancer. We have found out these values, the number one being 0.0078, the number second being 0.0298. This gives us an MAP that it's a non-cancerous tumor. So when the second test is done, this is first. So when the second test is done, it also gives us positive result, right? Therefore, we have two D1s. Therefore, we have to find H given D1 and D2, right? Now, as they are independent, this can be written as D1 given H, P of D2 given H into P of H by independence of data, because D1 and D2 are independent results, right? From here, we get positive given C, P of D2 would be also positive given C into P of C. Similarly, this would be, let's say, A, and our B would be defined as P of given not C multiplied by B of positive given not C into P of not C. Find out the values of these two, compare and take the max, right? If we take the max, we find, okay, I'll remove this part, we get left with, for A equation, we get 0.98 into 0.98 into 0.008, that gives us 0.0077, right? Similarly, for equation B, for given two positive tests but the cancer is not present, we are left with 0.03, and 0.992. This gives us 0.0009. We find that A is greater than B, therefore P of cancer given two positive tests is greater than P of not cancer given two positive tests. Therefore, the person has cancer. Now you must notice that at every step, these probabilities are getting smaller and smaller, right? This is because of log space calculation. This is just an additional detail. You can search on it. But that is how we reduce our hypothesis space to shorten down our possibilities.